Chapter 3 Stoichiometry of Formulas and Equations. Here are the main topics in this chapter: the moles, how to determine the formula of an unknown compound, how to write and balance chemical equations, how to calculate the quantities of reactant and product. In chemistry, there's an important concept called mole. The mole is defined as the amount of substance that contains the same number of entities as there are atoms in exactly 12 grams of carbon-12. So what is exactly the number of atoms in 12 grams of carbon-12? It turns out that the number is 6.022 times 10 to the 23rd power. So 12 grams carbon-12 contains 6.022 times 10 to the 23rd power carbon-12 atoms. The entities refer to atoms, ions, molecules, formula units, electrons, or any type of particle. For example, we can say 1 mole of hydrogen atom. So the entity is a hydrogen atom. So that means we have 6.022 times 10 to the 23rd hydrogen atoms. Okay, we can say 1 mole of water molecule. So in this case, entity is water molecule. We have 6.022 times 10 to the 23rd power water molecules. Okay, we can even say 1 mole of pizza. And that means we have 6.022 times 10 to the 23rd power pizzas. Now this number, also called Avogadro's number. Okay, so here we can say this is Avogadro's number. Avogadro's number equals 6.022 times 10 to the 23rd and is abbreviated as N. Okay, so we can say we have Avogadro's number of water molecules, and that means we have this 6.022 times 10 to the 23rd power water molecules. The molar mass, abbreviated as M, of a substance is the mass per mole of its entities. This includes atoms, molecules, or formula units. For monatomic elements, the molar mass is the same as the atomic mass in gram per mole. This is extremely important. For example, in the last chapter, we learned that in periodic table, the numbers give you atomic mass unit. For example, beryllium has the mass 9.012 atomic mass unit. And now we know that 1 mole of beryllium weighs same number but in gram. So 1 mole of beryllium weighs 9.012 grams. So the molar mass of beryllium is 9.012 gram. Similarly, hydrogen molar mass is 1.008 gram, and the lithium, 1 mole lithium molar mass is 6.941 gram. For molecular elements and for compounds, the formula is needed to determine the molar mass. For oxygen molecule, because it has 2 oxygen atoms, the mass of this molecule is 2 times mass of oxygen atom. And from periodic table, you can find the atomic mass for oxygen is 16 grams per mole. So times 2 give you 32 grams per mole. Okay, so that's the molar mass of oxygen molecule. For sulfur dioxide, since it has 1 sulfur, 2 oxygen, so you need to use 1 times mass of sulfur and 2 times mass of oxygen. And again, use periodic table, find the mass of the atoms and add together, give you 64 grams per mole. Here shows how to interconvert between moles, mass, and the number of chemical entities. Suppose we have a number of moles. How do we convert to mass? So we have 2 moles of hydrogen atom. The question is how many grams of hydrogen atom? Okay, we use molar mass as a conversion factor. So for example, for hydrogen atom is 1 mole hydrogen atom weighs about 1 gram. If you look at the periodic table, okay, you will find the molar mass for hydrogen is about 1 gram. So using this molar mass as a conversion factor, so moles hydrogen cancel each other, you get grams. Okay, you use 2 times 1, so that's 2 grams. Okay, so you use molar mass to convert moles to grams. Now, if we have more mass, how do we know moles? Okay, so again, we have 4 grams of hydrogen. How many moles of hydrogen? Okay, so we still use the molar mass, but this time we need to invert it. So this time we use 1 mole here, 1 mole hydrogen, 1 gram hydrogen. So this way, gram of hydrogen and gram of hydrogen cancel each other, you get moles. All right, so 4 times 1 is 4, so you have 4 moles of hydrogen. So interconverting between mass, moles, or moles and mass, you use molar mass as a conversion factor. Now, if we know the number of moles, how do we know how many entities? For example, 2 moles, again, 2 moles of hydrogen, how many number of hydrogen atoms? Okay, we know moles. How many number of hydrogen atoms? Now this time we use Avogadro's number as a conversion factor, and that is 1 mole of hydrogen equals 6.022 times 10 to the 23rd hydrogen atom. So in this case, 1 mole hydrogen and this number of hydrogen atom. Okay, so that's the definition of Avogadro's number. So using this conversion factor, moles cancel, you get the number of hydrogen atom. Now if we know number of entities to convert to moles, we also use Avogadro's number, but this time we invert it. So 1 mole equals this number of entity. So the number of entity in this case may be number of hydrogen here, number of hydrogen cancel each other, and that gives you number of moles. Okay. As shown in the last slide, to convert between mass and number of moles, we use molar mass as a conversion factor. Molar mass is grams per mole. So we can convert between moles and grams. Now from number of moles to number of entities, it can be atoms or molecules. Then we use Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd number of entities, maybe atoms, maybe molecules, per mole. Okay, so from moles to atoms or from atoms to moles, we can use this Avogadro's number as a conversion factor. Sample problem 3.1. Silver is used in jewelry and tableware, but no longer in US coins. How many grams of silver are in 0.0342 mole of silver? So the given is number of moles. The question is how many grams. So we are converting moles to grams. And from last slide, we know we need a molar mass. Okay, so in periodic table, we can find 1 mole silver, 107.9 gram of silver. That's the molar mass. And we need to use as a conversion factor because we want to cancel number of moles and we want grams. So we should write as moles on the bottom, and one more 107.9 gram of silver, so that the moles cancel each other and give you how many grams. So here we start with the given number of moles, multiply this conversion factor, okay, and then use 0.0342 times 107.9 give you the answer. Sample problem 3.2. Gallium is a key element in solar panels, calculators, and other light-sensitive electronic devices. How many gallium atoms are in 2.85 times 10 to the minus 3 moles of gallium? So the given is number of moles of gallium. The question is how many gallium atoms. We're converting moles to the number of entities. And for that, we need Avogadro's number. Avogadro's number here is 1 mole gallium equals 6.022 times 10 to the 23rd power gallium atoms. In order to cancel number of moles to give number of atoms, the conversion factor should write 1 mole gallium atom on the bottom, 6.022 times 10 to the 23rd gallium atom on the top. So the moles and the moles cancel each other, and that gives you gallium atoms. Sample problem 3.3. Iron is the main component of steel and is therefore the most important metal in society. It is also essential in the body. How many iron atoms are in 95.8 gram of iron? So the given is grams of iron. The question is how many atoms. We're converting grams to number of entities. And there's no direct connection between grams and number of entities. But we can convert grams to moles. Okay, so we have molar mass to convert between these two. And then we also can convert moles to number of entities using the Avogadro's number. So our plan is we need to do 2 steps. So the first step, mass to moles, use molar mass. From periodic table, you can find 55.85 grams iron is 1 mole iron. Okay, and then use a molar Avogadro's number to convert moles to number of iron atoms. So we start with given is 95.8 grams of atom. We write conversion factor, which is just the molar mass. Now note that we write the grams on the bottom. Okay, 55.85 gram iron, because we can cancel grams, and the unit desired is moles. So that gives you more iron. Okay, now using these moles, we convert to number of atoms. We use Avogadro's number. So we use 1 mole equals 6.022 times 10 to the 23rd atom at. So moles iron cancel each other, give you number of atoms of iron. As you can see, number of moles is essential for the conversion between grams, molecules, number of molecules, and number of elements. Okay, so for example, if we know grams of methane, okay, we can convert to number of moles of methane first, and then from number of moles we can find number of molecules. Number of molecules of methane. Okay, we can also find number of moles of carbon element in the compound or number of hydrogen element in the compound. Molar mass is for conversion between mass and moles. Avogadro's number is used for the moles to number of entities. Chemical formula is used for conversion between moles of molecule to moles of elements. Sample problem 3.4. Nitrogen dioxide is a component of urban smog that forms from the gases in car exhausts. How many molecules are in 8.92 grams of nitrogen dioxide? So we're converting grams, the mass, to number of entities. In this case is the molecules. As we saw in the last slide, we first need to convert grams to moles. So grams to moles using molar mass. And so we have to find the molar mass. So first we write the formula, okay, nitrogen dioxide, and then calculate the molar mass, and then find the number of moles. From moles, we convert to number of molecules using Avogadro's number. Here is the solution. First, we write the formula NO2, calculate the molar mass, mass of nitrogen times 1, mass of oxygen times 2. Molar mass is 46.01. Now using molar mass, we convert grams to moles. So we start with grams, and then we multiply by conversion factor. We write the 46.01 grams of NO2 on the bottom, 1 mole NO2 on the top. So gram cancel. That gives you moles of NO2. Okay, next we convert moles to number of molecules. So we start with moles, okay, and times conversion factor. So 1 mole, so moles cancel, give you number of molecules. And the answer is 1.17 times 10 to the 23rd power molecules. Sample problem 3.5. Ammonium carbonate, a white solid that decomposes on warming, is a component of baking powder. How many formula units are in 41.6 grams of ammonium carbonate? Ammonium carbonate is an ionic compound, and that's why here ask for formula units instead of molecules. So we are converting grams, the mass, to the number of entities. And we know we need to first go to moles to change grams to moles, and then moles to formula units. So we need to calculate the molar mass. So first we need to calculate, so write the formula and calculate molar mass. Here you have 2 nitrogen and 8 hydrogen, 1 carbon, 3 oxygen. So the formula mass is 96.09 gram per mole. We use molar mass of the formula units to convert the grams to number of moles of the formula units. And multiply by the Avogadro's number, we get number of formula units. Each formula unit has 3 oxygen atoms. Use this as a conversion factor. We convert the number of formula units to number of oxygen atoms. Here shows how to calculate the mass percent from the chemical formula. For example, water have a molecular formula H2O. So in each molecule, we have 2 hydrogen and 1 oxygen. To calculate hydrogen mass percent, we look at 1 molecule and we use 2 hydrogen atom times atomic mass atomic mass of hydrogen. So hydrogen in atomic mass unit, because we look at one molecule and two hydrogen, and then divide by the molecular mass of the compound water. So atomic mass unit. So again, we are looking at one molecule. So that's how we calculate. And then you need to times 100 to get percentage. Okay, that's the first method. We look at one molecule. Second method, we look at 1 mole of the molecules. So 1 mole of the molecule contains 2 moles of water. Of hydrogen atom. So to calculate hydrogen percent, we use 2 moles. So now 2 means moles times molar mass of hydrogen, which is gram per mole. Okay, you use molar mass of hydrogen and then divide by the molar mass of water. So in this case, it's gram per mole. Okay, so one look at one molecule, one look at 1 mole of the molecule. You use molar mass. Sample problem 3.6. The effectiveness of fertilizers depends on their nitrogen content. Ammonium nitrate is a common fertilizer. What is the mass percent of each element in ammonium nitrate? So we want to calculate the mass percent of each element in ammonium nitrate. So before we calculate, we need to know the molecular formula so that we can first find how many moles of elements, each element in 1 mole of ammonium nitrate. Okay, and then we multiply by their molar mass to get the mass of each element in 1 mole of ammonium nitrate. And then we divide by the mass of the molar mass of the molecule to get the mass percent, a fraction here. When you divide by the molar mass, first you get a fraction, which is a mass fraction of each element in ammonium nitrate. And in the last step, you need to times 100, and that gives you percentage. Let's calculate the mass percent of nitrogen element. The formula ammonium nitrate is NH4NO3. So in this molecule, we have 2 nitrogen and 4 hydrogen and 3 oxygen. And therefore, in 1 mole of the formula, we have 2 moles nitrogen, 4 moles hydrogen, 3 moles oxygen. To calculate the mass of nitrogen in the molecule or the formula, we use 2 moles of nitrogen times the molar mass of nitrogen, which is 14.01 gram of nitrogen per mole of nitrogen. And that gives you 28.02 grams of nitrogen. So that's the mass of nitrogen in 1 mole of the formula units. So next, we need to calculate the mass of 1 mole of ammonium nitrate. And so we use 2 times mass of nitrogen and 4 times mass of hydrogen and 3 times the mass of oxygen in molar mass. Okay, so that gives you 80.05 gram per mole. So next we calculate the mass fraction of nitrogen by the mass of nitrogen divided by the mass of 1 mole of the formula, which is 28.02 gram divided by 80.05 gram of the formula. That gives you 0.35. So that's the first calculation, give you the fraction. And then you times 100. Okay, when you times 100, and you get 35. And that's the percent, mass percent of nitrogen, okay, in the compound. So next, we calculate hydrogen. We do the same procedures. So the number of moles hydrogen times mass of hydrogen, molar mass of hydrogen atom, and divide by the mass of 1 mole of the formula, and you should get then times 100. Okay, that gives you 5.037% of hydrogen. And finally, we calculate the oxygen. Same procedure, you get 59.96. Mass fraction can be written as a conversion factor, as shown here. 1 mole, the mass of 1 mole of the compound, the mass of a certain element in this compound, 1 mole of this compound. By writing as a conversion factor, we can convert the mass of the compound into the mass of a certain element in that compound. Sample problem 3.7. Use the information from sample problem 3.6 to determine the mass of nitrogen in 650 grams of ammonium nitrate. We want to convert grams of a compound, the mass of a compound, to a mass of element nitrogen in the compound. So we need write the mass fraction of nitrogen as a conversion factor. We can convert grams of compound to grams of nitrogen. Let's write the mass fraction of nitrogen. It is the mass of 1 mole of ammonium nitrate, 2 moles of the mass of nitrogen atoms. So in this case, we already know the mass of the compound is 80.05 grams, which has 28.02 grams of nitrogen. So 2 times 14.01. That's the mass, molar mass of nitrogen. So this is the fraction, mass fraction of nitrogen. Now, using this as a conversion factor, we start with the mass of the compound. In this case, is 650 grams of the compound. So the compound gram cancel each other, and that gives you grams of nitrogen. Okay, so the answer is 228 grams of nitrogen. Now you use the numbers 650 times 28.02 divided by 80.05, give you this number, and the unit is grams of nitrogen. Now in the last question, sample problem 3.6, we already calculated the mass percent of nitrogen is 35%. Okay, we can use this also as a conversion factor, and 35% in mass means 100 grams of the compound and ammonium nitrate contains 35 grams of nitrogen. So use this as a conversion factor. We can also cancel grams of ammonium nitrate. We get grams of nitrogen, and so you can use 650 times 35 divided by 100. You should get the same answer. When we perform chemical analysis, we usually get empirical formula. For example, hydrogen peroxide has a molecular formula H2O2. That means within a molecule, there are 2 oxygen connected to 2 hydrogen. So this is a molecule with 2 oxygen, 2 hydrogen. But when we do chemical analysis, what we get is the ratio between the 2 elements. For example, hydrogen over oxygen, the ratio is 1 to 1. So based on the chemical analysis, we can write the empirical formula is HO, because the ratio is 1 to 1. That's all we know from chemical analysis. And this is called the empirical formula, which is the simplest formula for a compound agrees with elementary analysis. It shows the lowest whole number of moles and give the relative number of atoms of each element present. But the molecular formula shows the actual number of atoms of each element in a molecule of the compound. Sample problem 3.8. A sample of unknown compound contains 0.21 mole of zinc, 0.14 mole of phosphorus, 0.56 moles of oxygen. What is empirical formula? So we have moles of each element. We need to find the relative number of moles of each element. We divide by the lowest mole amount to give the relative mole ratio, which is the empirical formula. We first use the numbers of moles given. We write the preliminary formula, which is zinc contains 0.21 moles, phosphorus 0.14, oxygen 0.56. So this is called preliminary formula that comes from the numbers given. Next, we divide each fraction by the smallest one. So in this case, smallest one is 0.14. So each number divided by 0.14. The first one give you 1.5, the second one just 1, and the third one give you 4. And now we have a formula is zinc 1.5, phosphorus 1.0, oxygen 4.0. Note that you still have a fraction here. We need to convert fraction into a whole number. So what we do is we multiply by the smallest integer that gives the whole numbers. In this case, 1.5, you need to times 2. So smallest whole number is 2. Smallest integer is 2. And so that gives you 1.5 times 2 is 3. But don't forget, if 1.5 times 2, other numbers also times 2. So 1 times 2 is 2. 4 times 2 is 8. So that gives you the empirical formula. Okay, and you can check that the ratio in this formula 3/2/8 should equal to here 1.5/1.0/4.0, which equals to here 0.14, 0.14, or 0.21, 0.14, and 0.56. The ratio doesn't change, but we get the smallest whole number in empirical formula. Sample problem 3.9. Analysis of a sample of an ionic compound yields 2.82 grams of sodium, 4.35 grams of chlorine, 7.83 grams of oxygen. What is the empirical formula and the name of the compound? Compare with problem 3.8. You can see here are grams of each element given instead of number of moles. But first we need to calculate the moles of each element, and then we find the relative number of moles of each element divided by the lowest mole amount to find the relative mole ratios. We first calculate the moles of each element by dividing by the molar mass. So sodium divided by 22.99. So gram cancel, give you moles of sodium. And similarly, we calculate moles of chlorine, moles of oxygen. We follow the same procedure as last time. We write the preliminary formula, which is sodium 0.123, and the chlorine 0.123, and oxygen 0.489, and the smallest is 0.123. So divided by this number, you get sodium 1, chlorine 1, oxygen, you get 3.98. And note that this is very close to 4. And when we do chemical analysis, you always induce small errors. And so this can be just approximately is 4. And so the formula should be empirical formula, just sodium, chlorine, oxygen 4. Okay, and that's actually the sodium perchlorate. The molecular formula gives the actual numbers of moles of each element present in 1 mole of compound. The molecular formula is a whole number multiple of the empirical formula. As an example, hydrogen peroxide has a molecular formula H2O2, but the empirical formula shows the ratio is 1 to 1. So HO is the empirical formula, and the molecular formula is a whole number multiple, which in this case is two times of empirical formula. And because the molecular formula is twice empirical formula, the mass of the molecular formula, one molecule, is also twice of the mass of the empirical formula. So if we know molar mass, okay, using the molar mass of the molecule divided by empirical formula mass, you can find the whole number. In this case is the 2. Sample problem 3.10. During excessive physical activity, lactic acid forms in muscle tissues and is responsible for muscle soreness. Elementary analysis show that this compound has 40% mass of carbon, 6.71 mass percent of hydrogen, 53.3 mass percent of oxygen. Determine the empirical formula and determine the molecular formula. So our plan is, we first assume it's 100 grams of sample, and then each sample have a gram equal to the percentage. For example, carbon will be 40 grams, hydrogen will be 6.7 grams, and oxygen will be 53.3 grams. With these masses of each element, we can calculate the moles, the relative moles, so we can find the empirical formula. So how do we find the molecular formula? We use the molar mass divided by the mass of empirical mass. In the mass of empirical formula, we get the whole number, which times empirical formula give you the molecular formula. We assume it's 100 grams, so we have 40 grams carbon divided by molar mass of carbon give you the moles of carbon. Similarly, we calculate the moles of hydrogen, moles of oxygen, and the smallest number is 3.33. So divide by 3.33, we get the ratio 1 to 1. And so the empirical formula is carbon, hydrogen 2, and oxygen 1. And to calculate the whole number, we use the molar mass of this molecule, which is 90.08, divided by mass of the empirical formula is 30.03, and that gives you 3. And then use 3 times the empirical formula, give you the molecular formula, carbon 3, hydrogen 6, oxygen 3. Sample problem 11. When 1 gram sample of vitamin C is placed in a combustion chamber and burned, the following data are obtained. Mass of carbon dioxide absorbed after combustion is 85.35 grams. Mass of carbon dioxide absorbed before combustion is 83.85 grams. So this difference must come from the combustion reaction. And the mass of water absorbed after combustion is 37.96 grams, and the mass of water absorbed before combustion equals 37.55 grams, and the difference is the water produced in the combustion chamber. So this is CO2. Note that the carbon dioxide produced must come from the vitamin C, and the hydrogen also comes from vitamin C in water produced due to the reaction. But the oxygen is not. Not all oxygen comes from combustion, or from vitamin C, because combustion you provide oxygen. So vitamin C plus oxygen forms these two compounds. So the oxygen comes from, some of the oxygen comes from the atmosphere, and some come from vitamin itself. So what we do is, the mass of CO2 and water produced will give us the mass of carbon and hydrogen present in original sample. From those, we can determine the mass of oxygen. Let's calculate the grams of each element. We start with carbon, so calculate the difference of CO2 before and after reaction. So this 1.5 gram is the carbon dioxide generated by combustion reaction. And we want to calculate how many grams of carbon in this 1.5 gram of carbon dioxide. So we use the fraction of carbon as a conversion factor. Fraction is every 44.01 gram carbon dioxide. This is 1 mole of the molecule, which give you 12.01 gram of carbon. That's the molar mass of carbon in carbon dioxide. And then you use that as conversion factor multiply by 1.5 gram of carbon dioxide. So gram carbon dioxide cancel each other. That gives you gram of carbon. Similarly, you calculate the grams of hydrogen. So water is 0.41, and you use a fraction, the mass fraction of hydrogen in water as a conversion factor. You calculate the grams of hydrogen. And now the rest will be oxygen. So the total mass is 1 gram sample minus hydrogen minus carbon minus hydrogen, and give you grams of oxygen. So with these grams, we can calculate the moles, and then we can calculate the empirical formula. As we have done before, we use grams divide by molar mass of carbon, give you the moles of carbon, moles of hydrogen, moles of oxygen, and the smallest 0.0341. So you divide by that one. So the ratio is 1 here divided by 0.0341 give you 1.3, and this is also 1. So you have preliminary formula: carbon 1, hydrogen 1.3, oxygen 1. All right, and then you times a whole number, a small integer to give you a whole number. So integer is 3. 3.9 is approximately 4, and so that gives you carbon 3, hydrogen 4, oxygen 3. And to find the molecular formula, you use the molar mass given divided by the mass of empirical divided by this mass, give you 2. So 2 times empirical formula, and that's the molecular formula. As we have seen, molecular formula usually is different from empirical formula. Sometimes different compounds have the same empirical formula but different molecular formula. So here we show formaldehyde. The molecular formula is ch02o. Empirical formula equals the molecular formula. Acetic acid, molecular formula C2H4O2. The ratio is also 1 to 1. So the empirical formula is also CH2O. So empirical formula of acetic acid is the same as formaldehyde. Lactic acid, the molecular formula C3H6O3, the ratio is also 1 to 1. So it has the same empirical formula. These compounds, they all have the same empirical formula but different molecular formula, and they have totally different properties.